This video will be on Chapter 9, Circular Motion. Circular motion is tricky stuff. Really read the chapter carefully. It's easy to read, lots of good definitions, really think about what it means. So I'm just going to go over some of the basic ideas here. So let's talk about circular motions. That means we're going in a circle. Circles have a radius. Let's call that R for the radius. And when you're going in a circle, let's say you're going this way. So let's say you're swinging something around in a circle. So there's our little rock that we're swinging in a circle that way. So how fast is it actually going? Like right at that point, at that exact time, it's going this way at a certain speed. So they call that the velocity it's going at. You can call it the tangential velocity because it's tangent to the circle. That's what they call it. But it's just the regular velocity. How fast is it going right there? Well, it depends on two things. It depends on how long your string is and how fast it's going in a circle, how many circles per second you're going, or how many revolutions per second that you're going. So the way that's written is the tangential velocity, or its actual velocity, is equal to how fast it's going in a circle, which is the angular speed, which is given this letter omega. It looks kind of like velocity, but it's in an angle. It's kind of like curvy, maybe. It looks more like an angle. I don't know. So that's the Greek letter omega. Omega times the radius. So omega is called the angular velocity, and it looks like a W, but it's more curvy, and sometimes mine look like W's. It's the angular velocity. You can use whatever units you like. It can be in degrees. How many degrees per second, but the most common one is how many radians per second. And this is why it's nice to have pre-calc to kind of understand radians. There are 2 pi radians in a circle. Radians is the most natural unit to measure degrees, to measure angles in. There's 2 pi in a circle because the circumference of a circle is 2 pi r, so it makes sense. So if you go 1 circle per second, so you swing this thing around once every second, 1 circle per second, that's the same thing as a revolution, right? That's 1 revolution. A revolution is a circle, so 1 revolution per second, which is the same thing then as 2 pi radians per second, because 1 circle is 2 pi radians. Which means 1 radian is pretty small. 1 radian is like around 58 degrees or something. So a radian is something like that. So we'll say about, well, it's not 58. It's something about 58 degrees. And the way you get from degrees per radians is there are pi radians is the same, or 2 pi radians is 1 circle, which is 360 degrees. The 2 can divide out, so is pi over 180, so pi radians divided by 180 degrees. Or if you want to go the other way, it's 180 degrees by pi radians. So that's like 3, right? Pi is about 3, so it's 60, but pi is a little bit bigger than 3, it's 3.14, so that's where I get about 58 degrees per radian, something like that. About 58 degrees per radian. So that's where that comes from. Okay, so if you know the number of radians per second, how fast it's actually going is the number of radians per second times the radius. That's why the omega works really well there. Okay, so revolutions, a circle is a revolution. So if you know the number of revolutions per second, then you know the number of seconds per revolution. The frequency f, which makes sense, is typically the number of revolutions per second. So the period t, how long it takes per circle, is the number of seconds, all right, number there, number of seconds per revolution, which is just 1 over the frequency. So the period is 1 over the frequency. If you want to know how long it takes, it's 1 over the frequency, or so those work either way. The period is 1 over the frequency, or the frequency is 1 over the period. And a period is for the whole cycle. In this case, we're going in circles, so we're going once around in a circle. Now, if you want to know, this is the period in circles per second. If we want to know, or the frequency in circles per second, which is typically hertz, revolutions per second, we say how many hertz it's going in. A lot of times people use per minute for engines and stuff, RPMs, how many times your circle cycles through in a minute. So you can see RPMs. You got to be really careful in this chapter with minutes and seconds. This is RPMs, this is revolutions per second. Now, if you know the frequency in revolutions per second, then omega is just 2 pi times that. So if you're going 1 circle per second, F is 1, omega, the number of radians per second, is just 2 pi times 1. So it's what, 6.28 radians per second, which makes sense. If you're going 1 circle every second, you're going 2 pi radians a second, because there's 2 pi radians in a circle. So that's also one way. If you know the number of, if you know one, you can figure out the other one, which can be useful. So let's give an example here. Let's say that in our circle, we're moving in a circle at, let's say we're going, okay, let me write down an example here and make this official. Let's say we're going 5 revolutions per second, and the radius of our circle is 10 meters. So how fast are you actually going? Well, let's see, we just said that our velocity, how fast you're going in that circle, is omega r. 5 revolutions per second, that's the frequency. So omega is equal to 2 pi times the frequency, which is 2 pi times 5 revolutions per second, which is just 10 pi. I'm just going to leave it as a pi. 10 pi radians per second. So this is 10 pi times r, which is 10 meters. So that's easy. That's 100 pi. So 100 pi, pi is 3.14. So about what, 314. And we have meters and seconds. So it's 314 meters per second. So if you're going 10 meter circle 5 times a second, you're going around 5 times a second, and the circle's radius is 10 meters, you're going about 314 meters a second, which is really, really fast. Because you can imagine, 10 meter radius, that's times 2 pi, about 6.28, that's like 62.8 meters in one circle, and you're doing that 5 times a second. So the other way to look at it, if you don't like this formula, is like I just said. So one circle is 2 pi r, which is 2 pi times 10 meters, which is 20 pi meters. And we're doing 5 of those a second, 5 revolutions per second. So 5 of those per second, so our velocity is 5 times 20 pi meters per second, which again is 100 pi meters per second, which is like we got before, 314 meters per second. So that's kind of a more easier way to think about it, not just using a formula, but this works really well too. Just remember, a circle is 2 pi r. One circle is 2 pi r distance, right? The circumference of a circle. That's going to come up a whole lot because we're dealing with circles. Okay, another major concept of this chapter is the idea of centripetal acceleration, or centripetal force versus centrifugal force. So what keeps you going in a circle? Like if you're driving your car and you want to turn right, so here you're driving your car and you want to turn right, what makes you go in that circle? So if you're in your car, so here you are in your car, you feel like there's something pushing you. You want to go straight, okay? Your car wants to go straight. So there has to be something making it go in a circle. Okay? So what people think is that there is some force that's pushing them to the outside. Like if you're right here in your car, here you are, you're in the passenger seat, and you start going in a circle, you feel like there's a force pushing on your door, right? Your door starts pushing on you because that's what it feels like. But that's called a centrifugal force. It feels like something's pushing you. But really what's happening is you want to go straight, and so to make you go in a circle, something has to push you this way. It has to push you to the side in. So really it's that you're wanting to go straight. The car door says, nope, you're not going straight. And so you're pushing on the car door in a sense to get you to go in that straight line. Did I do that wrong? Let's see. If you're going this way, you're going in a circle there. You turn to the right. Actually, okay, I'm totally messed up, right? It's going the other way. You feel like you want to go in a straight line. Something is making you go this way. That's called a centripetal force. It's keeping you going in this direction. In this case, it's this driver. Okay, sorry about that. This driver feels the car door pushing on. The driver feels the car door pushing on him, and so making him go towards the center of the circle, and that's called a centripetal force. The centripetal force is always directed towards the center of the circle. So otherwise you'll go straight, right? So what in this case, it's friction of the car tires or of the person here. It's the door, because the door is connected to the car, making them go in a circle. That's called a centripetal force, versus a centrifugal force is what people think it's pushing to the outside, but that's not the way it works. To go in a circle, something has to force you to go in a circle. Friction, something like that. The centripetal acceleration, which we won't derive, but how fast you're accelerating when you go in a circle, is your velocity squared, how fast you're going. So you're going a certain velocity as you turn, divided by the radius of the circle. So maybe here's the radius of the circle. You're going a certain speed in your car. That's your centripetal acceleration. The centripetal force, and this little c stands for centripetal, is just the mass times the centripetal acceleration, which is mv squared over r. So if you're swinging your rock around here at a radius r, and you're swinging it, and it's going, let's say, 10 meters per second, and let's say it's a 2-meter long rope, what is the tension? How strong does this rope have to be, or how strong are you pulling it inwards? Because you're pulling it inwards. You know, when you're swinging that thing in a circle, you can feel it pulling on you. You got to pull really hard inwards. So what force are you going to have to exert? So the force, and let's say it's a, I don't know, let's say 3 kilogram rock. Okay, you have a 3 kilogram rock. So the centripetal force is mv squared over r. Mass is 3. V is 10, so 10 squared divided by the radius is 2. Let's see, 100 divided by 2 is 50, so that's 150. And like always, it'll be newtons because we have meters, kilograms, meters, seconds, or meters down here, meter squared per second squared here. So it's 150 newtons. So you're going to have to be pulling in with 150 newtons. If you put a spring scale on that rope that you're swinging around, and you read the reading in the spring scale, it would read 150 newtons. And the acceleration, how fast it's accelerating towards the center of the circle, is just the v squared over r part. So the centripetal acceleration is the v squared over r. That's what, 100 divided by 2. So it'd be 50 meters per second squared, which is a big acceleration. And acceleration means you're changing your velocity, right? You're changing your direction. You're going in a circle, so you're changing your direction here, which means you're accelerating. Even though you're going the same speed, that's what's kind of weird. You're accelerating because you're changing your direction, which takes a big force to change your direction. If this was a car, we did the same things, but instead of a rock, it was a car. That'd be the force the tires have to exert on the car to keep it going in a circle. Okay, that's a summary kind of a section of chapter 9. Again, I suggest you really read it to help you understand it. And thanks for listening.